Hello students, in this video we'll discuss what open sets of the real line are with respect to the metric topology. So if we're given a subset O contained in R, we say that O is open, and this of course is with respect to the metric topology. If for every point A in O, there is an epsilon greater than 0, such that the interval A minus epsilon to A plus epsilon is contained in the set O. In other words, a set is open, here's the real line, a set is open if I can take a point inside that set A and I can squeeze in a small open interval centered around A that remains entirely in that set. And so as is illustrated over here, we can show the following results. So here's a proposition. AB, the open interval AV, is open. And the proof of that is relatively straightforward. If we let X be in the set AB, then if epsilon is less than the minimum of B minus X and X minus A, then X minus epsilon to X plus epsilon will be contained in the interval AB. That's easy to see analytically, but it's also easier to see geometrically. Namely, if I just pick here's A and then here's B, and then here's a point X, well, clearly this distance over here is going to be the smaller distance over here. So if I pick an epsilon that's smaller than that distance, that interval will be stuck inside the interval AB, and that proves that the open interval AB is an open set. In fact, open sets, this is a prototypical example of an open set. And we have the following result about these open sets too. This is an important result. Proposition: arbitrary unions and finite intersections of open sets are also open. Okay, that's easy to see. So the proof of that fact is the following. The proof of this proposition is that if AI are open, and we consider the set A capital, which is the union over I and I of AI. If X is in A, then X is in AI for some I. And therefore, that tells me that there is an epsilon such that X minus epsilon, X plus epsilon is contained in AI for some epsilon. And therefore, X minus epsilon to X plus epsilon, if it's contained in AI, it's definitely contained in A because A is the union. And that proves that this union is open. So that's the first part of our statement, that arbitrary unions, it didn't matter how large my indexing set was, as long as that X is in one of the open sets, there's going to be an interval that's contained in that open set that will be contained in the bigger union. And finally, for intersections, we can see what to do. For intersections, if A1 through AN are open, and X is in the intersection, I goes from 1 to N of AI, then what we can do is the following. For each of these I, we can say that X minus epsilon I, X plus epsilon I will be contained in AI for some epsilon I greater than 0. And if we take our epsilon just to be the minimum of epsilon 1 through epsilon n, that's still greater than 0, the minimum of a finite collection of things is still greater than 0, then we can see that X minus epsilon to X plus epsilon is going to be contained in X minus epsilon I to x plus epsilon I for all I, and therefore this interval over here is going to be contained in what? That's going to be contained in the intersection. I goes from 1 to n of our set. And so that proves that our set, the finite intersection of open sets, is open. And interestingly enough, so if I have this condition over here, finite intersections of open sets are open, arbitrary union, together one final condition, namely that the empty set and the whole set are open, tells us that with these three statements that the metric topology is actually what's known as a topology. Those are the conditions for that open sets have to satisfy for that subsets of R to be a topology. Thank you very much.